usual, Patrick and I have just decided what we're going to teach now. No.
We've been thinking about it for decades.
No, not quite, but we're still planning this through as we go along. Today I'm going to introduce, what we're going to do today, I'm going to introduce another concept. We're going to talk about genetic algorithms, but really the whole area of evolutionary computing. Just very light, touching on some of the big concepts here. Patrick will talk about it again. And then what is going to happen over the next few lectures, we're going to be assigning you some work to do, and we'll talk a little bit about that at the end. And we're going to let the work and discussions you guys have lead the next few lectures a little bit. So we'll talk a little bit about that at the end and how we're going to do that. So this is the last time I'll probably stand here with a more telling you about some technology. I'm going to introduce genetic algorithms. I stole this PowerPoint from someone in Israel. I was online looking for introductions to genetic algorithms, and this was freely available online, so I thought, I'll use this. And what are genetic algorithms? Well, probabilistic optimization. Probably doesn't mean a lot to some of you, but a lot of problems that we try to solve, we solve using optimization. We're trying to optimize something. So it could be trying to find the strongest weld we can use on a bridge structure. We're trying to optimize that strength. We could be optimizing the lowest cost to produce a piece of plastic. We're often trying to optimize to gain solutions. And we have all sorts of mathematical techniques to optimize things. This method of optimization is inspired by evolution, using the kind of concepts Darwin first thought of natural selection and genetic inheritance. Originally developed by a very interesting guy, John Holland, back in 1975. John Holland did a lot of work on snail brains and things like that. He developed this concept of genetic algorithms. They're very suited for hard problems, problems that we can't solve using traditional methods of search. And also, if we don't know a lot about how to solve the problem, these kind of genetic algorithms work well as well. They are now a standard technique in business, science, engineering to solve problems. They're very good as well where we have an enormous search space that can't be solved by, we can't search the whole space to find the best solution. The kind of search techniques we normally have, we use calculus-based techniques, we use numerical techniques. We have these kind of what we call more intelligent techniques or guided techniques like hill climbing. And the evolutionary algorithms fall down into the bottom here, the genetic kind of ideas. So, how do they work? The way it works is we think about evolution. You have a whole population of animals, some of which are stronger than others, fitter than others, better than others in some way, some of which are weaker or not strong. And this population breeds with each other, and the ones that are better adapted to the environment tend to have a better chance of survival. And the ones that are weaker probably die out. And so we do the same thing. We generate a population of solutions to the problem, and we apply operators to it. Now, the operators we apply are the ones from evolution. So we have a selection operator, which means the ones that fit the environment have a higher chance of being selected to survive. We have recombination, which is the equivalent of breeding. It's also called crossover. where we take two solutions, they breed and they swap their genetic material. A mutation, where we have little random changes in the whole population. So it all sounds very abstract. You can kind of visualize it with animals, but how would you do this with a computer? So think about the natural environment. In nature, we have an environment. With a genetic algorithm, we have a problem we want to solve. Let's imagine we want to find the lowest cost, highest strength tower structure to put a mobile antenna on. And there's all different ways we can build this tower, different types of materials, different sizes. So we need to optimize this. And there are millions of different towers we can build. Now, we have individuals that live, the population, individuals that live in that environment. Here we have a whole list of different towers we can build. We have each individual in nature is adapted to their environment. They may be particularly suited, they may be poorly suited. Here we have towers that may be strong and cheap, or we may have poor towers that are weak and very expensive. But we can assess how good those towers are. We have a population, so we have hundreds of thousands of these animals, insects, whichever population. Here we have the same thing, we have thousands and thousands of towers. Here, these animals interact with each other. Some die, some survive in the environment, some breed with each other, some mutate. We do the same things to our towers. And over generations, the whole species or the whole population becomes better suited to that environment. Here, over many generations, the towers become better suited to whatever parameters we've set, strength, low cost, whatever. So, what we're doing is we have simple versions of the real biological mechanisms. But what will happen is, because we have such a large population, we will generate all sorts of interesting structures and solutions using these algorithms. But what we will do is we will evolve a solution to our problem. So, the way it works, we produce an initial population of individuals. Usually these are rubbish, they don't work very well. We evaluate how good they all are, and then we see which ones survive, we let them breed, we mutate, and we see how good our new solutions are and generate a new population, then go back here, and we just go through generation after generation of solutions. I'm going to show you some examples of this. So, basically, we have, it's a looping kind of system. We are, we start with our initial population, we decide which ones survive and which ones die off. We have a kind of breeding area. We evaluate those, not breeding and mutation. We evaluate the new one, create our new population, and loop around this again. Until with the evaluation, we're losing members of the population as well. So, what I'm going to do is show you, hopefully, a few examples of this in practice. So let's have a bit of an explanation of it first, hopefully. This is a